Rail survey techniques. Today I'm going to talk about different rail surveying techniques, including static scanning, kinematic survey and scanning, unmanned aircraft system, ground penetrating radar, and then we're going to summarize at the end. Railroad safety protocols. Rail surveyors typically work through tough conditions and are therefore required to complete the applicable rail safety training courses. They work near active railroad tracks, in dark tunnels, with rats sometimes, on crowded transit platforms, in confined spaces during the night, and also subject to multiple remobilizations to accommodate passing trains and flagman protection. These tough conditions need to be addressed prior to commencing work to ensure safety is paramount. One thing I like to mention is I'm going to present a broad overview of various rail surveying techniques that are available to engineers, architects, and owners. I like to point out that I am not a surveyor. My background is in rail engineering. I've been doing rail engineering for about 30 years now. For engineers, architects, and owners, it's important to know what surveying techniques and emerging technologies are available to support their specific project type. And it's my goal to present these so you have a better understanding of your surveying options. We will not be getting into too much detail about the technologies or the process. Those would be subsequent presentations. However, should you have specific detailed questions, feel free to contact me at the end with the email address, and we'll definitely get back to you with some answers. I'd like to start off with some static scanning. Static scanning is the first surveying technique I'd like to present to you. The surveyor uses a laser scanner that is set up at specific locations to collect millions of points of existing data. These points are then organized into 3D point cloud where features can be extracted into CAD for the development of existing plan to be used for design. They can go into either AutoCAD or MicroStation. This is a terrific way to survey station platforms, whether on the surface or underground, and many other railroad-related facilities, including shops and yards. We can also survey vertical circulation, stairwells, elevators, escalators, etc. In addition, since utilities and cable conduits and cable trays can also be scanned, electrical and mechanical engineers can also benefit from this technology. The point cloud data can be used to create a BIM model, Revit, and in addition, images can be taken and incorporated into TrueView. This will help designers get a good visual of the existing conditions. Here are some static scanning examples. If you look to the left there, we can scan wayside objects, signal huts, signal mast, overhead catenary system, poles, all kinds of information and features along the rail corridor. In the middle there, we can also show that we can scan overhead utilities for clearances. A lot of times, maybe on a light rail project or something, it's crossing under these high tension wires and we need to get the proper clearance. We can scan that too. And even rail tunnel caverns, you can scan those with the static scanner. You could also scan it with the mobile scanner. We'll talk about that a little bit later, but it's very helpful to get some good data using the static scanner in rail tunnel caverns, particularly if they're under construction too and you're doing as-built surveys. Here's another example of an underground station platform that was scanned. And as you can see, you can even notice the detail with the tactile warning strip at the edge of the platform. You have the cables up above, the structure is clearly evident, the columns, the third rail on the track, the rails, the ties, all of that information is captured from the static scanning. And then it's converted into 3D CAD files for use of designers. The next one I want to talk about is kinematic scanning. It's broken up into two parts. First is mobile mapping and includes the use of LiDAR equipment similar to the static scanner. However, this is attached to either a high rail vehicle or a train. Similar to static scanning, the data is collected using laser that will convert millions of into a 3D cloud where features can be extracted to produce CAD drawings and digital terrain models. Speeds can vary. The faster you go, the less points you get, the less density in the point cloud. However, this is an excellent way to survey rail corridors, particularly for the use of design of passing siding track. So if you got a 2-mile passing siding track that you want to design for a freight railroad, you want to get survey 3 miles of track, put the LiDAR equipment on top of that high rail vehicle, you get excellent data for the entire corridor, and then you can convert that into topographic maps. As you can see, there's accuracy about 0.04 feet with the mobile mapper. And of course, you still have to come back and do some conventional surveys for identifying culverts and invert elevations and other utilities that will not be captured with the mobile LiDAR. Another thing that you can do with the mobile LiDAR is capture features that wayside features can be imported into GIS, asset management programs. Other important features such as OCS wires and structures and overhead transmission lines can also be surveyed using this methodology as well. Another thing that you can use the mobile LiDAR for is streetcar design, particularly if you're in a planning stage and you want to get information about the corridor for your streetcar. You can attach this to a regular pickup truck and drive the streets and collect survey data, such as curbs, buildings, bridges, bridge clearances. Another thing that's very important is overhead wires and utilities, and even traffic signals. I've worked on projects in the past where traffic signals need to be raised to accommodate the streetcar OCS wires. The second one I want to explain is AMBERG trolley. This piece of surveying equipment can be used to accurately survey tracks. The points collected can then be used to develop a regress horizontal and vertical alignment where existing circular curves, spirals, vertical curves, and super elevation can be determined. It can also be used to analyze clearances and tunnels between track centers, clearances between other structures, and it also uses a laser similar to that described on mobile LiDAR. Now, as you can see in that picture down below, that's a manually pushed piece of equipment. We have to take that in consideration when we choose that methodology of survey. Here's some examples of mobile mapping. On the left there is a LiDAR scanner, and you can see on the top as a Ladybird camera, and that can get images similar to Google Earth, 360-degree view. The middle photo is a transit station above ground, and you can clearly see the OCS wires and all the other utilities and platform edges and so on. And we've extracted some of those features and overlaid them on the point cloud so you can see what we intend to do with such data, with point cloud data. The view on the right shows a rail corridor within rock cut. A lot of times there's slope issues that we have to deal with, and this mobile LiDAR can capture that information. Here's some other examples using the mobile mapping. The picture on the left shows a situation where the new vehicles on this particular project are bigger, and as they go around that curve, they would collide, so they have to wait until the other one passes. So this particular study used mobile LiDAR to collect data to identify the exact location of the track within these curves, so that we could determine what needs to be modified on the track geometry so that the trains, the mid-ordinate and end vehicle overhangs will not collide. On the right here is a vertical bridge clearance example. The mobile mapping can get the girders underneath, bottom beams, and we can get the clearances, and that's always important when we're doing resurfacing of tracks or designing new tracks. You also clearly see the graffiti on the abutment. Here's a situation where we describe how this equipment is attached to the vehicles. On the left is where it's attached to a train, an actual train with those brackets that have been placed on the end. And so the train operator will push forward on the train, and the data collector would be on board. And then on the right shows an equipment mounted on a high rail vehicle. You can see in the back there, that's the equipment placed on there. We go onto the track, and then we proceed forward and collect data. So we have those opportunities to mount. Here's an example of some tunnel mapping that has been done. On the left is a cross-sectional view, and you can see the track and the center lines have been extracted. And we extract that with a template that we push through with a software called TopoDot. And we could determine where the center line of track is, and then we could regress that at alignment and get the geometry both horizontally and vertically. You could also see in the top, we can do things like obtain the tunnel crown and produce a break line for it. And all those features that you see there, including the structures and the cables, we can extract all of that information. And it's very helpful when determining clearances. On the right is an example of showing how that extraction three-dimensional data looks in a CAD format. Here are some examples where we can use the AMBERG trolley. If you see on the left there, that's a streetcar project and there's a bit of a kink in the road. Contractor had bad survey in the beginning that caused an issue when laying out that rail. So we came with our AMBERG trolley and resurveyed it and came up with a recommendation on how to fix it. The AMBERG trolley is much more accurate than the mobile LiDAR. And so a case like this is very important to use this AMBERG trolley to get specific, accurate data on the alignment of that particular track. On the right is another example of a profile that's a PVI. The green line is the existing top of rail surveyed by AMBERG, and the white line is the proposed track. In this case, the track was lowered, so we can use the AMBERG trolley to determine ballast undercutting, concrete plinth replacement, and reprofiling with a regression analysis. Here's some other examples of the use of the AMBERG trolley. On the left there, that's a transit project where we're surveying the curve, and of course the safety measures are put in place, and we would determine what the super elevation is of that track. The middle is an example of showing how we can survey clearances. And you notice that little notch in the top there. That's because the freight trains are double stacked and they had to add that notch. So the AMBERG trolley was going to determine, make sure if that is indeed clear and there's no collisions. And we do that with our software, and we put the vehicle dynamic envelope in the software and process it to make sure there aren't any collisions with the surveyed tunnel. On the right shows an example of where we can use it for construction. We can help our contractors determine the as-built situation of the track that has been constructed. Here's some additional examples. We can do clearances and tunnels with the car body for transit. And then on the right shows a cross-sectional output of the car body clearances for freight in the tunnel, similar to what I showed earlier. Now we're going to talk about unmanned aircraft systems. This is kind of an emergent technology, and it's kind of exciting. The use of drones to support rail surveying is something new. LiDAR equipment can be attached to a vapor copter to survey a rail corridor. FRA approval to fly in the air is necessary. In addition, permission by the railroad owner will also be necessary. There's a lot of restrictions with this, and it may not apply to a particular program. However, it could be very cost effective to use this if warranted. In situations where we're doing survey along a track and we can't fly above the track, we can fly adjacent to the right of way. You can go one direction on one side of the right of way line and the other direction on the other side of the right of way. And the LiDAR will lap, and we have plenty of points to produce a topographic map. The use of drones can also be helpful in grade crossing inventories, vegetation control management, where we can use video to determine where trees overgrow over the tracks and required to get cut down. We can also use them for disaster relief, such as storms or train derailments. And we need to take the drone, a smaller drone, not the copter, to get some images and help assess the situation. They could also be used to support track inspections. Here are some examples of unmanned aircraft system here. On the left is a grade crossing, and you can get good information about the type of grade crossing, what the grade crossing measures are. We could extract all that information if necessary and create an inventory. In the middle shows our vapor copter with LiDAR equipment attached to it. And then on the right, you can also use it for slope failure. We can get data, three-dimensional data on a slope that failed and use that data for mitigation measures. Here's an example of where we can utilize the UAS for supporting inspections. You still need boots on the ground for track inspections, but this can really help out on some other situations, and you can see how clear the images can be. Now, there'll be large file sizes, but nonetheless, you have the ability to get down into the bolts of the ties. You can determine information about the tie quality. You still have to go down there and do the visual inspection with boots on the ground, like I said, but this can certainly support it and maybe help create efficiencies in the track inspections. The last technology I'd like to introduce to everybody is ground penetrating radar. This is to support identifying a location of utility crossings and parallel underground utilities. It can also help determine subsurface track conditions. You can also attach this to a high rail vehicle or a train similar to the mobile LiDAR unit. The depth is about 8 feet. It can read below, and information obtained would include ballast moisture content, ballast depth, sub-ballast depth. Could also be used in conjunction with mobile LiDAR and geotechnical information to determine drainage issues, locations where ballast is fouled, etc. So using all these different tools together can help create a maintenance program for a particular railroad. In summary, safety is paramount. I just need to stress that because these are very dangerous conditions that surveyors work in. We have to respect that and accommodate that in our projects. Conventional survey is still very important. We still need to get invert elevations, utilities, anything that the LiDAR or any of the other tools cannot see. And you have to manually go out there and collect. Another reason why you need conventional survey for these projects is for the survey control. You have to tie all of that information with the real world coordinates. So some additional things that are required with conventional survey is placing targets. So mobile LiDAR and static scanning, you need targets that are surveyed so you can, when you see them in your point cloud data, you can tie them to the survey control. And in some cases, a project may be too small or some other reason. You would do it all conventional survey. You may not want to choose one of the other methods to do to survey your project. That's still okay. we still need to use conventional survey. It might be the most cost-effective way to survey your particular project. So in conclusion, there are many tools in the toolbox for surveying railroads and their stations and all the rest of the infrastructure related to it. You got to work with your surveyor to determine the most appropriate rail survey technique for your specific rail project. You might use a combination of all, or you might just use one. Whatever is the best, cost-effective, and safe. All of those things need to be considered in your survey. So that is the end of my presentation. I appreciate everybody listening in. I hope this some of this strikes some interest in folks. And if you have any particular questions, feel free to send it to that email listed down there, and we'll send it to the appropriate experts, and we'll provide a response. Thank you very much.
Thank you, Kevin. This is Maria. We have a few questions from our audience. So the first question is from Jim, and his question is, how do you achieve a point of 0.04 feet of accuracy with mobile LiDAR?
Okay, thanks, Maria. So what we do there is we overlap our coverage. So we get a lot of points and create greater density of the points. And you also have to make sure your survey control is tied into it and you have targets that are closely placed to each other. If you have targets along the corridor that are a mile apart, your accuracy goes down. If they're closer, a couple of 100 feet apart, your accuracy goes up. So it all has to do with the density and the tie-in with the targets that are controlled by ground survey.
Okay, thank you. Thank you. Another question is from Sina, and her question is, what antenna frequency do you use for GPR?
That's a good question, and I don't know the answer to that, and I will get back to you with that answer when I talk to the appropriate expert on that.
Okay, great. And we have the email, so we will definitely communicate our answer back. Another question here is from Charles, and his question is, can LiDAR and GPR be collected at the same time?
Yes, they can. You can have a high-rail vehicle that attaches the LiDAR equipment in the trunk, in the back, and then you could attach the GPR equipment in the front. And the GPR equipment has three components to it. You have one in the middle that collects data between the rails, and then you have two on the side that collects data on the outside of the rails. Thank you.
Okay, and it looks like just one more question. This is from David, and his question is, are you able to fly a drone over an active railway?
Thanks, David. Good question. You can fly it over an active railroad if they allow it. And the FRAA, there's no FRAA, I'm sorry, FAA restrictions. But since the railroad is owned, for the owner of the railroad, you have to get permission to do that. And really, I would prefer to have the drone fly on the side of the right-of-way, just to create some safety buffer. So you would fly the drone adjacent to the right-of-way line going one direction, collect data, and you turn around and you do the same on the opposite side to collect data. They overlap in the middle. That would be a better approach than flying over the active track. We're not allowed to fly over active roadways and highways, so I don't think a railroad would want us to do that over their active track. So thank you for that question. Appreciate it.
Okay, that should do it with the questions over here.
Okay, great. Well, thanks everybody. Really appreciate it, and have an excellent day. Thank you very much.